So we have seen that for this kind of a I section that we have, when it is applied to a shear, which applied to a shear force P. So let's say in this case your P is nothing but equals to V that you see over here. The flow of the shear happens parallel to the element side, and it is also like the flow of water. So if your V is acting vertically down, you're going to have the overall dimension. So let me just quickly mark it. It is going to happen something like this. So parallel to the sides of the flange at the top, and parallel to the web in the middle, and the flange again at the bottom, just like the flow of water, it just flows out, right? Now what we are trying to find is what is the magnitude of this Q. Is it going to be maximum at the ends and maximum at the centers and so on? So let's take a look. So for this, you have this cross section over here, right? Now here, remember that since the sections are thin walled, since the thickness is usually very thin, usually most of the dimensions are marked center to center, because the edge dimensions are essentially very small. So that's why you have a h over 2 over here. So we are going to start in deriving this formulation first for the flange. Now remember, the flange is this top part over here. So this is my flange, and of course this guy is my web. So first, if we start with the flange, so what I'm going to do in the flange, I'm going to take a small chunk of it, so along essentially this section BB. So my section of interest is this small chunk that you see over here, similar to something like this over here. So if I take this one, you see this small yellow portion which I've marked over here. I'm just trying to find that what is the the arrow that is over here, what is the Q which is going to act over there, what is the magnitude of that Q, that is what I'm trying to find. So essentially my section of interest is this one, and I'm trying to find that at this edge, that where I have drawn this section BB over here, what is the value of the Q that I'm getting here. So Q may be in the flange, Q or tau in the flange, what is the value of that I'm trying to get, right? So let's go ahead and try to write that one over here. Now you see, to find this Q, remember that our generic formula. So if I write it out, I have the Q of flange is going to be V Q divided by I. Now I is a property of the section, so I'm not going to tinker around with that. V is the applied shear. So the element of interest is this guy Q over here, right? So the Q is essentially, since this is my section of interest, remember Q for this particular section that I get over here is simply going to be equal to the area of the section. Q is A prime times Y bar prime, the area of the section A prime, and Y bar prime is the distance of the centroid from the neutral axis, which is H over 2 over here. So let's just write it out, that what is my Q going to be. So Q in this case is going to be the area of that chunk is S times this thickness TF over here. So it is going to be S times TF, right, times, so this is my A prime, times it is going to be your H over 2, right? So this is Y bar prime. Okay, so now that I have this, let us put it back in the formula and see what it comes out to. So I have my Q of F. If you do a slightly a bit of rearrangement, so what you will get is that S T of F H V over 2I. Okay, so this is my formulation for the Q of. See that one particular thing, note that this is a function of S. So what does it essentially mean? It essentially means that at the edge where S equals to 0, Q equals to 0, and it slowly peaks up as you reach towards the center. Now since this is a doubly symmetric section, doubly symmetric meaning that it is symmetric about this axis, symmetric about this axis over here, it actually suffices to just look at 1/4 of this one over here. So we'll just do it for 1/4. So here you see that S is 0, so Q equals to 0, and it slowly peaks up and becomes a maximum at this particular point over here. Now for this one, if you're going from this side, you essentially have to replicate the similar kind of an exercise. So here let's just go ahead and maybe mark this one. So this is my value of Q of F that I get. Now remember, what is the relationship between Q and tau? I know that the relationship between Q and tau is that my Q equals to your tau times T, right? So this is the relationship we know. Now since we're looking at the flange over here with the thickness of TF, so your tau of F, so that is the shear stress in the flange, it is going to be related to the Q in the flange that you see over here. So this also essentially gives you the relation that your tau equals to q divided by t over here. So if I just write it out, that tau of f, right? So my tau of f is going to be q of f divided by the t of f. So essentially this t of f, goes for a toss over here. So what you get, the simplified relationship as s h v divided by 2I. So this is the shear force which you get in the flange, which is over there. Now note that, very important, note that, and we will mark it out, we will draw it out later. Note that the value of the q and the tau both is essentially 0 at the edge, and it also makes sense in certain perspective. I will tell you why. So if you see at this guy again, you see here I don't have any shear at this particular face, right? So that essentially means that this complementary shear must also be 0. So it's that's what you get exactly at that particular edge. If you see exactly at this edge over here, the tau is 0, q is 0, and as you slowly go in, it is a linearly varying function of s that you see over here. Okay, so that takes care of the flange over here. So it is going to go from 0 over here to have a linear increase. So if you have to draw the magnitude of q, let me just magnitude of q or magnitude of tau. So let me try to sort of roughly mark it. So it is going to go from 0 at this edge to a maximum value over here. So this is just the magnitude, not the representation of the direction or so on. Similarly, for the other side, you are going to have a 0 over here, and it is going to peak up to something over here, right? Okay, now let's come to the web. Now for the web part, let's write the web. Web is the vertical portion that you see over here. Now for the web, suppose if I'm trying to find the q which is acting over here, remember for the web I know this q is acting vertically down. So for the web, say if I try to find the q exactly at the interface over here. So if I'm trying to find the q of the web at this interface, right? So let's maybe make a note that so at the interface with the flange. So if you take that one over here, similarly you have the q of f equals to vq divided by I again. Now so let's just maybe go ahead and write that first, the generic formula. Right now you see in this particular case I'm again not going to touch my v, not going to touch my I. Now q, what does q happen? Now since I'm calculating over here, the entire section above it encompasses, it comes. So it's essentially wherever you're trying to calculate the q, whatever section you have left behind. So here you're trying to calculate it over here, whatever section you have left behind was this one. Here since you're calculating here, whatever section you have left behind is essentially this, say the whole of the top part over there. So let me make this figure maybe a bit more messy. So essentially this is the whole thing which you're looking at, right? So for that one, if you compute, so here your q is going to be what? It is going to be this entire area, that is s times this. So s is going to be, so this one over here. So this is this whole thing. So that is the width of the web, that is b times tf. So q is going to be b, sorry, yeah, let's color is fine, b times tf. So this is the area, and the distance from here to to the neutral axis. So since this is a very thin walled section, this distance can be taken simply as h over 2, that is fine. So btf times h over 2 that you get over here. So now if you back substitute in this one, what this expression essentially gives you is that your q of w, but remember this is at the interface between with the flange. What you get is that b times tf times h v divided by 2I, right? So this is the value of q that you get at the interface. Now if you go a little bit further down the section over here, instead of calculating here, if you calculate it slightly below exactly at the over here, so exactly at the centroid, you can derive. And if I take a distance r, and a similar way I try to derive, and you can take a look at a textbook of how to get that one. I'm simply going to write the formulation over here, since you know already how to derive these formulations. What I will get, that at that particular point, I think here I did one mistake, because No, this is fine. So this I wrote QW over here. Now in this case also I wrote your tau of the flange. So for this correspondingly at the interface, if I write at the tau of the web, how does this look like? So tau at the web, remember, is Q divided by T, but here my T, the tau at the web over here, is this thickness over here, that is the TW. So how is this going to look? Is this going to look like? So it is going to be QW divided by TW. So that essentially becomes equals to BTFHV by 2TW times I. Right, so this is the shear, but again the shear at the interface between the flange and the web that you see over there. Okay, so now this was at the interface. Now, as I was saying, if you come to the centroid over here, the value of the Q and the value of the tau, I'm going to write it. I have it derived here already. So the at the middle of the web, the value of the tau W, it comes out as something like this. So at middle, and you can derive this easily, middle of flange, at middle of web, at the middle of web. So that is at C over here at this particular point. If you calculate it over there, your tau at web comes out as, this is a slightly elaborate formula, so I'm not going to go into the details of that, BHTF divided by TW, and you will see it boils down to the earlier formula we derived. I'll show you in a minute. Plus H square by 4 minus R square times V divided by 2I. So this is the generic formula, and you see that it's dependent on this R over here. Now, as I was saying, if you are putting R equals to H over 2, that is if you're trying to derive the shear, if you put R equals to H over 2, that is you're trying to derive the shear at this particular point, you see it becomes H square by 4, this one cancels, and eventually it becomes BHTF V divided by 2ITW, which is essentially this one. So this is what's at the interface. So this is the general formula which you can derive, or you can derive the one for the interface here separately, right? So now putting everything back together, so let me show you maybe a cleaner page where all the formulas which we derived are already written out, so which is something like this over here. So what we derived, that at the flange over here, right? So this is the, you remember the magnitude which we draw. We did not draw this one, but now it will be clear to you. So you see at the flange over here, it is SHV by 2I dependent on S. So at the edges, it is going to be 0, and it is going to be maximum at the center over here. Remember, once again, it is extremely important to note that these are representations of magnitude, not of the direction. So it just means that 0 over here, maximum over here. It does not mean it is going vertically down. At the flange, it is acting parallel to these edges over here. Okay, so this was for the flange, and if you take a look at the web over here, right, at the web, this is what we derived. This is the same formula which we derived. If you just remember, BHTAV divided by 2ITW. If you just go back, this is essentially what BTHV divided by 2T W times I, which is exactly what you have over here, and this is the Q of the web, right, at this interface, at this particular place. And at the center, this is tau W. We can derive a QW at the center as well. It is not done over here. So this becomes the maximum at the middle of the web. Why it becomes the maximum? This again takes you back to the concept of that rectangular face which we were saying. Remember, it is minimum at the top and the bottom, and it is maximum at the center. We had done a similar example for this one, in which also you had looked at a I section, but that I section was not a thin wall. It's a slightly thicker wall I section that we looked at, right? There also, if you remember, there was a jump over here, and then we reached the maximum thing over here. Now here also, remember, this ordinates that you see, it is only representative of the magnitude. It is not representative of the direction that you have. So maybe it's better to explicitly write this down. So what you see over here, these guys are only so this represents only the magnitude and not the direction that you see over here. Okay, so what I want you to have a takeaway from this, instead of remembering all these numbers and so on, because you can easily derive, we'll do a problem example where we derive this, is that the shear flow, it happens parallel to the edges over here of the flange as well as the web over here. Now also, In the flange, it is 0 at the edges and peaks to the maximum at the center. At the flange also, it is the minimum is at the interface and it peaks to the maximum at the center, and the flow is just like the flow of water that you see over here. Okay, so now let's again make a note. So this is what I was saying, and also one very interesting point that you will realize here. You see that this is just like the flow of water which I was saying, this V over here. So you see at this particular point in the flange, so this, if you're pouring water from the top, right, it comes over here, and this one, you know, it merges. This water comes from here it merges. So here the volume of water, you know, analogically the volume, quote unquote volume of water, must have both this one and this one. So it must be Q1 plus Q2. So does it happen in our case? Let's take a look. So here you see at this particular point, which is at B over 2, which we derived, right, where S was equals to B over 2. So let's go back to the previous page. See, at here S was equals to B over 2. So if you put this guy back over here, what is this ordinate that you get for the Q? So the ordinate for the Q that you get is that, I will write it over here, that Q at F at B over 2 becomes equals to, so if I put S equals to B over 2 over here, so that becomes B H T F V divided by 4I. Right. So what I am saying, that here the magnitude of this one, of this arrow just at this point at the center at B over 2 is this one. The magnitude of this arrow is over the same. Now if this is just like the flow of water, if these two have to mix together and flow into this one, the magnitude of this one must be twice, because these two are equal. The magnitude of this must be twice, right? And for this one, at this region at the wave, we have already found this one. You see the magnitude of this one is exactly twice of what you have over here. This was BH2FV by divided by 4I. If you multiply with 2, this you get BHTFV divided by 2I. So it is just like the flow of water. This is essentially what it shows you over here. Q1 and Q2 here, both are the, you know, equal in magnitude. So these two are the same over here, and both of them sort of merge together, and eventually this Q which you get at this interface, it becomes equal, right? So, and you also, one important thing you note from this magnitude or from the length of the arrows itself, it is very negligible over here. You have a smaller arrow at the edges, it peaks up at the center. These two arrows, the length of this arrow is essentially the double of this one, because it sort of merges together. And here at the center, this tau or the Q is maximum. So you have the biggest arrow over here, it reaches back over here, and essentially the water flows out something like this, right? So overall, to note is that, so this is the nutshell, that the shear flow, it has linear variation in the segments which are perpendicular to V. So this is the V over here. Oops, sorry. So mark that accidentally. So if you have this V over here, this is the section which is perpendicular to V. That is the flange over here. Here the variation is linear. You see, it starts from 0, it linearly varies, whereas in the section which is parallel to V, which is essentially the web, the parallel to V, you have this parabolic variation over here. Here also it is minimum at this interface, and it reaches the maximum over here. So now that we have an overall understanding of how the shear flow essentially happens, let's go ahead and take a look at a problem example. Maybe not an I section, we'll take a look at a box section, a box beam that we have. So to make these ideas more clear, we are going to draw out what is the variation of Q, what is the variation of tau for that particular one. So hang on, we'll go on to the problem example.